Hello everybody. So what I'd like to talk about in this video is I'd like to talk a little bit about how you can plot continuous distributions using R. So if we go into the week 5 notes, just to kind of show you the previous video that I did for discrete distributions, if you go into week 5 and go into the extra or optional material, I have a link here to a video that talks about how to plot discrete probability distribution graphs. So in this video, the binomial distribution was discussed, as well as the geometric distribution, which you guys don't need to know. That was for a different class, but it talks a little bit about how to plot discrete distributions in R. Today what we're going to talk about is how to do this for continuous distributions, and it's going to be basically the same thing, except now we're going to be focusing on our two continuous distributions, which are the exponential and the normal. So just a quick thing to mention before I continue here. As far as needing to know how to plot these distributions for something like a quiz or an exam, you are not required to know how to do this in R. This is mostly just for people who are curious. The main thing to remember about these distributions when we start talking about the continuous distributions is for an exponential random variable, an exponential distribution is generally highly right skewed. So this is page 6 of the 2.3 notes. In general, exponential distributions will have this shape, this nice right skewed shape, whereas normal distributions, let me find a picture here, on page 14, normal distributions have that nice symmetric shape, that bell curve shape centered at the mean of the distribution. So no matter what the mean is, no matter what the standard deviation is for a normal distribution, it will generally have this nice bell curve shape, and it will be symmetric about whatever the mean is. So as far as like takeaways for graphs for either of these distributions, exponential distributions are highly right skewed, normal distributions are symmetric and bell-shaped about the mean. But if you are curious about plotting these distributions and seeing what they look like for specific parameters, so like for specific values of beta for the exponential, or specific values of mu and sigma for the normal, you can keep watching and I'll show you how to do this using R. So let's actually go ahead and start with an exponential distribution. So I'm going to go back up to that example on page 11 here. And let's actually use this kind of intro picture here on page 6 and see if we can recreate this in R. It's going to look a little bit different than this one because this one has some nice shading in it, but it will look generally the same. And the idea is to give you some information about the general shape of the distribution itself. So we don't know what this is modeling, what variable we're dealing with, but we do know this is an example of an exponential distribution where beta equals 0.6. So let's go ahead and see how we would plot this using R. Let me just get that there in the corner here. So here's R, actually technically RStudio, but of course if you're just using plain old R, you can do this exact same thing. It would just all be in the R console. Here I'm going to be typing it in the in my upper window here in my R script, and then just sending it to the console, and then my plot is going to show up over here. So when we plot continuous random variables, just like we did for the discrete random variables, we're going to use the plot function. So the plot function takes, by default, two arguments, x and y. X is going to be whatever's plotted along your x-axis, and y is going to be whatever's plotted along your y-axis. You can also customize this plot function as we did with the discrete by saying what type of plot we want. I'll show you that here in a second, but let's just focus on our x and our y. So I'm just going to leave that up there just for reference. So on our x-axis, what we want is we want a range of values for our random variable. Now, depending on what your random variable is, and depending on your parameter or parameters as well, you might need a different range than the one I'm typing in here. But I can see that for this particular exponential distribution, it looks like, just from my reference picture, that once I hit a variable value of 5 here, it looks like my probability is pretty small. It gets pretty low. So what I'm going to do for my x-axis is I'm just going to plot values from 0 to 5. And the way that I'm going to do that in R is I'm going to type 0:5. So that's going to tell R that on my x-axis I want values from 0 to 5. Now for my y-axis, this is where we have to bring in information about the actual distribution, because this is where we're going to actually want to plot. Technically they're the densities of this distribution, but we're going to be able to see, this is incorrect, it should be densities, but we're going to be able to see what this actually looks like. So how do I incorporate the probabilities for this exponential distribution in this plot? Well, for the exponential distribution, we've learned a couple R functions. We've learned px and we've learned qx. Now, when we're plotting an exponential distribution like this, we're actually not going to use either one of these in our plot. We're actually going to use dx. So what this is going to do, and we saw the d functions when we were talking about discrete random variables, right? We saw like d Poisson or d hyper or d binom. We saw these types of functions back when we were dealing with discrete random variables. And what these gave us is it gave us the probability that x equaled a certain value that we had in that function. So this would give us the probability that the Poisson random variable equals 4, assuming we had a lambda here, or 7 or 1 or whatever we were interested in. As we've learned in the 2.3 notes, we don't really use these functions anymore because technically when we're talking about continuous random variables, when we're considering the probability of x exactly equals something, that's always going to be 0. So as far as the relationship between the dx versus like the d Poisson or d Poise, this will give us a probability, as will d hyper and d binom. This will give us a density, which is not quite the same thing, but it does allow us to plot the picture that we want. So I'm not going to go too much into density versus probability here, just because I don't want to move us too far off the main track here. We mostly just want to plot. That's all we want to do. So when we're plotting continuous random variables, then we can use the d function, so dx or d norm, as we'll see in a second. So let me go back to our example here. For my y-axis, I'm going to use the dx function. And this takes, just like all the other x functions, two things. It takes our value of interest, and it takes our 1 over beta parameter. So what I'm going to want to do, so I get no errors when I plot this, is for my x value here, so for my first argument to this dx function, I'm just going to put the same range of values that I'm putting on my x-axis, so 0 through 5. Then I'm going to put in my beta parameter. So my beta parameter is going to be 1 over my actual beta. So if you remember, let me just scroll down here. R calls this rate. It's 1 over beta. So for this example here, for my parameter, I'm going to say rate is 1 over my beta, 1 over 0.6 in this case. Now I'm going to exit out of that parenthesis for the dx function. I'm actually going to type one other thing here in this plot. Let me expand this. I'm going to tell this to be a certain type of plot. And specifically, I'm going to use type L. Now this is not necessary. You don't have to have this. But what this does is it actually makes a nice continuous line over all of these values of x, and it makes your plot actually look like a nice continuous distribution rather than something that's choppy or something that has points. So this again is not necessary, you don't have to do it. It just makes for a nicer looking plot and sometimes makes the plot easier to read. So let's see what we get. I'm going to open my plot window here. Now remember, if you're in R, the plot will open up in another window. So if you're using R for this, maybe I'll just show that after this. It will just pop up in another window. If you're using RStudio like I am here, make sure that your plots window here is bigger. In other words, don't make it all the way over here, or else R will say, oh, you don't have enough room to make the plot. Maybe put it like halfway. That way your plot will show up here without RStudio freaking out that there's not enough space to display the plot. So if you get an error when you're doing this, it might just be that your plot window is too small. So just drag that beam, the breaking point between those windows, over a little bit first. Okay, so let me go ahead and run this and see what we get. So this is what our plot looks like. Let me click on zoom to export that into something a little bit bigger here. So this is my plot. Now notice it looks a little bit choppy, and that's because in these arguments I am putting in integers. So I've got 0 through 5 as 0, 1, 2, 3, 4, 5. So R is kind of connecting the points here using that type equals L. But we can still see the general shape, right? It still looks very similar to the plot that we have here. It's just a little bit choppier. If I wanted to make this a little bit smoother, what I could do is I could just expand my number of values that I'm using. Let me close that plot here. So here we can see once we hit 5, most of these probabilities beyond that are going to be really, really small. But if I want a smoother curve here, what I could do is maybe try 10. And if I change my x-axis range here, I also want to change the range in the dx function. So if this is from 0 to 10, this should also be from 0 to 10, because if I don't, it's going to give me an error and say that the points on my x-axis, well, in this case, there's too many of them compared to the points that are plotting along my y-axis. So it's like I don't have enough x and y coordinates to match up. So R gives me an error. So that just means I need to change this to 10. And we can see when I expand that to 10, my plot gets a little bit less choppy, but you can see that once we get beyond about 5, you can see these probabilities are all going to be very, very small. Now, the other thing I want to show here is if I take this type equals L off, so just delete that, what do we get? Same thing, it's just now you can see it's all dots, it's all points. Which, it's not too hard to read that, but it's not, I don't think, as easy and as quick to read as when they're connected by the lines. So I always like to put in that type equals L, just to make it easier to read. For those of you who are using R, just plain old R, you can do this as well. Let me just copy this code so I don't have to type it again. Here's R. So here's my R console. I can just paste that into the R console, and notice that when I hit enter, it's just going to open my plot in a separate window. So here's my graphics window. Same exact thing as we saw, it's just a different plot. And you can close this and just go back to your R console. So it's the exact same thing, it just displays it a little bit differently than RStudio does. So let's actually do another example here just for some practice. Let's do the first example with the bus stop. So this is on page 7 of the 2.3 notes. And this was the example 2.3.1 where we were talking about the bus stop, and the waiting time for bus number 19 can be modeled by an exponential distribution with beta of 21 minutes. So if I wanted to plot what this distribution looks like, this exponential distribution, let me just actually copy this code again here and put it below. So the first thing I'm going to note is, okay, well, the first thing I'm going to change is my rate. So instead of 1 over this beta, I'm going to put 1 over this beta, 21. And then for my x-axis, notice that my beta is 21 minutes. So that's like my typical expected value of x. So as far as my values go on my x-axis, I'm actually going to want to go a decent ways beyond 21, because 21 is, for an exponential distribution, beta is our expected value. It's a typical value for the variable. So we would think that the probabilities beyond x equals 21 will be some sort of non-trivial values, right? They'll be relatively high. So let me just look and see what I have in my notes here. What did I use? I used 50. So I went from 0 to 50 here. And you can change that if you want to. If the plot looks weird or you want to double check it or play with the x-axis, that's perfectly fine. Let me change this to 50 as well, just so I don't get an error. And let's see what we get. So notice that I'm already having some issues. If I made my plot window too small over here, it's already giving me something about my margins. And if I try to plot this, just run this, R is going to be like, oh my gosh, I can't fit a plot over here. What are you doing? So I get a whole bunch of errors here, and it basically just means that my plot window is too squished. So if you see this and you're like, what the heck? It just means drag your plot window over a little bit and then try it again. There we go. So this is what this distribution looks like. And we can see there's that right skew shape again. So it starts with larger values of probability for smaller values of x, and then as x gets bigger and bigger and bigger, we can see that the area under this curve, if we just think of like from 40 to 50, is a lot smaller than the area under the curve between like 0 and 10. And again, I can experiment with this. Maybe I want to see maybe 70 instead of 50. So I need to change that in both the x-axis part and the dx part. And we can start to see, oh yeah, okay, as x gets bigger, we still get that right skew shape. We still see that right skew shape of this distribution. And it's such a fast process. You can change this to whatever you want and see what happens. Maybe not that high, but just, practice playing with the x-axis and the corresponding y-axis, and just see that you can get a good idea of that general shape of the distribution for pretty much any value of x that your random variable can assume. All right, so that's a couple exponential distributions. Let's look at some normal distributions, or at least one normal distribution. So I'm going to go back to the notes here. And I'm going to scroll down to a normal case. Okay, so this is the general shape of a normal distribution. And I'm actually going to just pick an example for this one, since it's now that we've kind of reintroduced how plotting works. Let's just do one example with a normal. And let's look at this example on page 16, 2.3.5, where we're looking at the Stanford-Binet IQ test. So this is a very typical distribution that's often used to introduce the normal distribution, because the Stanford-Binet IQ test was written to follow a normal distribution with a specific mean and a specific standard deviation. So this is very common to see this example in introductory stats courses where you're introducing the normal distribution. So let's actually plot this and see what it looks like. So let me put this over here for reference. All right, oops. So now we're going to plot a normal distribution. And I'm going to start the same way. I'm going to start with plot. Then I have my x-axis and my y-axis. So let's start with my x-axis. Now the thing to notice about the normal distribution here is the range of possible values is technically from negative infinity to positive infinity. Those are the values that a normal random variable could assume, or something in a normal distribution can assume. But the likely values of a normal distribution depend on their parameters, specifically the mean and the standard deviation. So I know from my knowledge of a normal distribution that this distribution is going to be centered at 100. And this distribution also has a standard deviation of 15. So let's actually start by plotting, just for practice, from one standard deviation below the mean to one standard deviation above the mean. So my mean is 100. If I go one standard deviation below the mean, that's 100 minus 15, that's 85. And one standard deviation above the mean is going to be 100 plus 15, which is 115. So let's just try that as my range for my x values for my x-axis and see what we get. Now for my y-axis, I have to do the same sort of a thing that we did up here. I have to match it with the values in my x-axis. And instead of dx here, I'm going to use dnorm. So for my x values in the dnorm function, I'm going to put the same ones that I have on my x-axis, so 85 through 115. Now remember that our normal functions, dnorm, pnorm, qnorm, as you can see that RStudio is telling me, it takes three things. It takes the argument for the value, it takes the mean parameter, and the standard deviation parameter. So in addition to these x values, I'm going to tell dnorm that the mean of this distribution is 100 and the standard deviation is 15. So just putting in the relevant parameters for my normal distribution. And then just like I did for the exponential here to make it easier to read, I'm going to say I want this to be type L. If I could type, there we go, to make it a little bit easier to read. So let's see what this looks like. So I'm going to run this plot, and it looks like that. So maybe not quite what we were expecting. We were expecting maybe something that looked a little bit more like all the drawings in the completed notes, where it's got that really nice bell curve shape. Here it just kind of looks like a dome. not super interesting. but like it doesn't quite look like this. But if I were to extend my x-axis out in both directions, maybe a couple more standard deviations in each direction, we would start to see more of this bell curve shape. So let's go back and edit our plot and see what else we can get. So rather than going, let me close this, rather than going one standard deviation out in either direction, let's go 3 and see what we get. So I'm going to copy this and just put it here. So my mean again is 100. So if I go 3 standard deviations below the mean, that's 3 times 15, which is 45. 100 minus 45 gives me 55. So 55 is 3 standard deviations below the mean. If I go 3 standard deviations above the mean, that's 15 times 3, 45. 100 plus 45 gives me 145 as my upper range for my x values here. So let's see what this plot looks like if I have 55 through 145. Now again, if I just try this, I'm going to get an error because I didn't change my denorm piece here. So if I see that error, I'm like, oh shoot, let me go back up here and change these so that they match. Okay, there we go. Now let's see what this looks like. Okay, now we're getting something that looks more like a normal distribution. We've got that nice bell curve shape. We can see the main mass of this distribution is at the mean, and it is centered and very nicely symmetric about the mean. Now, of course, I could keep going here if I wanted to maybe subtract another 2 standard deviations from this part. So this would become 25, and then 145 plus 30 would be 175. I mean, just to practice and see what the distribution would look like. There we can see that once we get kind of beyond those 3 standard deviations out, 55 to 145, we start to see really that flattening, meaning that if you go beyond 3 standard deviations away from the mean, the probability that you're going to have an IQ above 3 standard deviations above the mean or below 3 standard deviations below the mean gets really, really small. And even something like IQ of 3 standard deviations above the mean, that's 145, that's really high. But you can really see the dramatic drop here as you go beyond that even further. So again, just a way to visualize the distributions. So if you go back and look at that plotting discrete distributions video, you'll see a lot of this is basically the same as what we did before. It's just now we're using exp and norm for the exponential and the normal distribution instead of plots for the binomial, the hypergeometric, and the Poisson. But the process is about the same.